In this video, we will demonstrate how to perform titration calculations. A titration is the incremental addition of a titrant to an analyte. This is an analytical technique that is exclusive to solution chemistry. The titrant is a solution of known concentration added via a precise burette, and the analyte is usually of unknown concentration or unknown quantity. A titration is essentially measuring the stoichiometric ratios in which two compounds react. The products are usually of little interest. This method can be used to determine the quantity of an analyte to a very high precision. So depending on the precision of your burette, you can measure the volume of the titrant to either a 0.1 or a 0.01 milliliter quantity. Now there are many types of titrations. Typically, you can titrate an acid with a base, or a base with an acid. But you can also titrate, say, iron using potassium permanganate, performing a redox titration in order to determine the quantity of iron in a substance. Regardless of the type of titration that you perform, it is important to understand the calculations in order to avoid any errors, and therefore any consequences. In our first example, we're going to be titrating an acid, HCl, with a base, sodium hydroxide. This is one of the simplest titrations that you can perform. This is a simple acid-base neutralization reaction. This occurs in a 1-to-1 ratio of base to acid because sodium hydroxide is a monobasic base and hydrochloric acid is a monoprotic acid. But what's most important is to understand when you have added just the right amount of sodium hydroxide to completely consume all of the hydrochloric acid. How do we do that? Well, we need an indicator. One of the most common indicators in acid-base titrations is phenolphthalein. Phenolphthalein, here on the right, is colorless in an acidic solution. Therefore, if the pH of your solution is below about 7 or 8, you're going to see no color. So this is typically added to your analyte, and if your analyte is an acid with a pH lower than 7, then you're going to have a colorless solution. Now, as you add sodium hydroxide, eventually you're going to consume all of your hydrochloric acid. And then a very minute quantity of sodium hydroxide will be added. At that point, you will reach your end point, and the solution will turn just slightly pink. If you add too much sodium hydroxide, then the concentration of the colored version of phenolphthalein will be too great, and therefore you'll have a very deep purple or very dark pink solution. That way you know you've gone beyond your endpoint. The endpoint is the color change, which will alert you that you have added the exact same number of moles of base as moles of acid that are present in your analyte. So for instance, we want to calculate the concentration of an unknown hydrochloric acid solution when 35 milliliters of 0.2 molar sodium hydroxide solution was required to titrate a 5 milliliter sample of the unknown hydrochloric acid. So here's the reaction. Basically, we are going from concentration and volume of sodium hydroxide and trying to determine moles and then concentration of hydrochloric acid. So we know both volume and concentration of our sodium hydroxide, so we start there. But remember, concentration, molarity, is always in moles per liter, so we need to convert all of our volumes to liters. Once we have the volume in liters, we're going to multiply it times the concentration, which is in moles per liter. And since the reaction is a 1-to-1 ratio of sodium hydroxide to hydrochloric acid, we're going to convert those moles of sodium hydroxide to moles of hydrochloric acid. Check our dimensional analysis, and we're left with 7 times 10 to the negative 3 moles of hydrochloric acid. So what do we do with this information? Well, let's go back to the question. The question was asking the concentration. We took a 5 milliliter sample, and in that sample, there were 7 times 10 to the negative 3 moles. So if we want to find concentration, we take moles divided by liters. Now be careful, that was a 5 milliliter sample. We need to convert that to liters by dividing it by 1,000. So the concentration of the hydrochloric acid was 1.40 molar. Another common titration is the standardization of sodium hydroxide. Now, a sodium hydroxide solution is notorious for decomposing or degrading over time because it reacts with carbon dioxide and air. And carbon dioxide, when it mixes with water, forms carbonic acid. That carbonic acid is going to start neutralizing your sodium hydroxide. So it's very important to always know the exact concentration of your sodium hydroxide before you start a titration with it. This is typically done with potassium hydrogen phthalate, or KHP. Potassium hydrogen phthalate is preferred because this is a solid and it can be weighed out to a very high precision. KHP also is extremely stable. It does not degrade over time, and it does not absorb moisture. So, we are going to be titrating a 0.5123 gram sample of KHP, the formula is here, with our sodium hydroxide. We don't know the concentration of our sodium hydroxide, but we do know that it required 25.5 milliliters of sodium hydroxide to titrate our solid. So in this reaction, we need to find the number of moles of sodium hydroxide that was delivered during this titration. Since this is a 1-to-1 reaction, we're going to take our mass of KHP, and we need to calculate the molar mass, and then divide the mass by the molar mass. And then, again, since this is a 1-to-1 ratio, this tells us we have delivered 2.5086 times 10 to the negative 3 moles of sodium hydroxide. Now that we have the number of moles of sodium hydroxide that were used in this titration, we can divide that by the volume that we delivered. This is specifically the volume of sodium hydroxide. You notice that we have another volume in this problem. It said that the KHP was dissolved in about 20 milliliters of water. Well, it doesn't matter what the concentration of the KHP was. The KHP was a solid, and since we knew the mass, we knew the very high precision number of moles of KHP that was present. So taking the moles of sodium hydroxide that were dispensed based on the mass and moles of KHP divided by the volume of sodium hydroxide converted to liters, we have a concentration of 0.09838 molar sodium hydroxide. In our last example, we're going to be titrating iron with potassium permanganate. In this calculation, we've added an additional step. We need to actually determine the volume of potassium permanganate that was added during this titration. Now, burettes look a little different. The graduation marks are actually in reverse. In order to determine exactly what volume of titrant you've added, you need to take the final burette reading and subtract from that the initial burette reading. The initial burette reading here is, well, it's about 9.5. It's a little beyond 9.6. So if we want to estimate out one more decimal place beyond the last graduation, the initial burette reading is 9.62. If we look at the final burette reading, now this final burette reading is after we have performed the titration and we have reached our endpoint. The final burette reading is a little beyond 24.1, it's about 24.15. So if we subtract the initial from the final, we have a total volume added of 14.53 milliliters. So a total of 14.53 milliliters of 0.04897 molar potassium permanganate solution was required to titrate a 0.5442 gram of an unknown iron 2 compound in the presence of acid. Calculate the unknown compound's percent composition. Now, in order to calculate percent composition, we need to know the mass of iron and the mass of the unknown compound. Well, we know the mass of the unknown compound. Now we need to use our titration information to calculate the mass of the iron. We know how much potassium permanganate was added. We need to convert that to liters. We know the concentration of the potassium permanganate, so we can determine the number of moles of potassium permanganate added. Using the stoichiometry of the reaction, the 5-to-1 ratio of iron 2 to potassium permanganate, we now know the number of moles of iron that was titrated. Now we need to convert moles of iron to mass using the molar mass. And now that we have the mass of iron that we have titrated, we can divide that by the mass of the sample. We don't need to know what the sample was, we just need to know what the mass was. and according to our titration, this compound is 36.51% iron.